Hi everyone. So in this short video, I will give you a proof of uniqueness theorem 1. So maybe some students feel difficulty to understand this theorem. I hope after watching this video, you have all the clarity of this theorem, and I personally find this theorem quite interesting. So let's look the theorem. The theorem says the solution to Laplace equation in some volume curly V is uniquely determined if potential V is specified on the surface S. So before proceeding to proof, we have to look some basic concepts, which is Poisson equation equals to del square V equals to minus rho by epsilon naught, where V is your potential and rho is charge density. If charge density is 0, it becomes Laplace equation, which says del square V equals to 0. And by the basic calculus, you can say if some potential follow Laplace equation, that means no local maxima or minima allowed. And maybe you can write in comment section the reason of this consequence. It's from very basic calculus. And further, if there is some extrema, then that extrema exists only at the boundary. And for more details, maybe you can look this classical text written by Griffith. Maybe all of you know Griffith, third edition, Classical Electrodynamics, in short ED. Okay, so now we look the proof. Okay, so the last line of the statement is quite important. It says if V is specified on the surface S. So we define the potential inside the volume curly V. So I would say this volume is curly V. Okay, so these we define two potentials V1 and V2, which satisfies Laplacian equation. So which says del square V1 equals to 0, del square V2 equals to 0. Importantly, V1 and V2 are equal on the surface because this is the statement of our theorem. I hope you understand the first two lines. Now we define potential V3, which is equals to V1 minus V2. And in next step, I took Laplacian, which says del square V3 equals to del square V1 minus del square V2, and I can simply write it equals to 0. That means V3 also satisfies Laplace equation, but V3 equals to 0 on the surface. This is the most important point. Why V3 equals to 0 on the surface? Because due to our statement of the theorem, V1 and V2 are equal on the surface. If what theorem says? If V is specified on the surface S. That means on the surface we define the potential. Okay, so V1 equals to V2 equals to V. That means if V1 equals to V2, so V3 equals to 0. But this V3 equals to 0 on the surface, since V1 equals to V2. Now use this property. Since no local maxima and minima is allowed, so since no local maxima and minima is allowed, what it implies, and V3, so and if there is some extrema exists, this extrema exists only on the boundary. That means only on the surface. So if the extremum value on the surface is 0, that means inside the bulk, inside the volume, this value is also 0. Why? Because V3 follows Laplacian, and according to Laplacian, this property should be follow. That means V3 equals to 0 everywhere, implies inside the volume V3 also 0. But we define V3 as V1 minus V2. Okay, so V3 equals to 0 inside the volume. That means V1 minus V2 equals to 0. That means V1 equals to V2. So which implies if V1 and V2 equal on the surface, if we define a unique potential on the surface V, this uniqueness theorem says inside the volume V, there should be one and only one value of the potential V. I hope you understand this uniqueness theorem. You have to just follow this property. And if you follow this property, this uniqueness theorem can be easily proved. Okay, thanks for watching.